afternoon. I'm Jerome, and I lead the AI team here at Facebook. Thank you. So in this session, we're going to talk about PyTorch. For those who don't know PyTorch, it is the open source framework that we have developed to create AI at Facebook and for other people to create AI. Quick poll, who has heard of PyTorch before? All right, I would assume no. Who uses PyTorch? It's getting there. All right, so PyTorch is a deep learning framework that, let's see if that works, that we use for our engineers and researchers to develop new machine learning models, explore neural network architecture, and deploy them at scale in production, right? PyTorch started around 2.5 years ago as a project directed toward AI researchers. And it quickly caught on because of its ease of use, and really it facilitated exploration in deep learning. Now, last year at F8, we announced PyTorch 1.0, which is a unified framework that still serves the AI research community, but also combines that with the reliability and production tools that you need to be able to do AI at scale. Now, at Facebook, we use PyTorch everywhere. We use this unified framework really to accelerate the rate from which we take research and bring it to production. So for example, today, we use PyTorch 1.0 end-to-end to deploy and create all our natural language services and machine translation services, OK? And it's in a product like the Facebook app, or like here in M Assistant in Messenger, OK? Now, this system today provides around 6 billion translations a day. And thanks to the flexibility of PyTorch, we're able to actually iterate very quickly. So today, if you were at the main keynote, Shreb talked about self-supervision. And we are deploying this self-supervision research in production just a matter of weeks after it has been created. Now, PyTorch is not just about Facebook. It's really a thriving community that's growing around it. And that includes anybody from people, developers starting to get acquainted with AI, to some of the best-known AI researchers, and some of the best-known companies doing AI. It's the second fastest-growing open-source repository on GitHub. And we're really super excited to see a growing number of companies using PyTorch for research and for production. Now, today, we're really fortunate to have representatives from 4 of these companies, Microsoft, Airbnb, Genentech, and Toyota Research Institute, and they'll tell us how PyTorch is helping them build, train, deploy production-ready AI. So to get us started, I'm going to call to the stage David Aronczyk, who's from Microsoft, to tell us how they use PyTorch to create machine learning model at scale.
Thank you very much. I feel like I get to cheat because you all are full and happy, and that just it means you're going to judge me better. So as Jerome said, I'm Dave Aronczyk. I lead open source machine learning strategy at Azure, and I do a bunch of work in ML ops. And previously to this, I was the lead PM on Kubernetes, and I started the Kubeflow project. And so I really understand the value of a fast-growing, deep community around open source machine learning. And that's exactly what we're seeing at PyTorch. At Microsoft, we've been doing machine learning for a long time. We have one of the largest research arms in the world, and we made tremendous progress around machine learning, not just for ourselves, but really to help the research community. And you can see just a few of the real milestones that we were able to launch over the past 2 years in vision and speech and language. Some of these were world records at the time. And of course, we gave it all back because it's so important that we help the entire industry move forward for machine learning. But like I said, it's not just about open source or not just about machine learning giving back. We also use this internally. You can see here over 180 million users use Office AI features today. On Cortana, we get 18 billion queries, and we analyze over 6.5 trillion security events every day on behalf of our users. And the reality is that ML at Microsoft is what makes this possible. We could not do this. We could not process this volume of data if we did not have the advancements around machine learning and the performance and other characteristics. So, okay. And though I mentioned just a few of the advancements, AI and ML touch literally every product at Microsoft. Every consumer, client app, server side, games, research, Bing. We use ML in all of these categories because it's so important to us to use this massive volume of data in an intelligent way. I want to dive into one of these specific examples. I mentioned the 18 billion queries Cortana processes, and what you see behind that is a lot of our NLP work. Previously we had individual groups starting up their own NLP work to process all this incoming data, and it was fine, but it did lead to a bunch of duplication and other issues that we were going to have trouble getting through, and it really hurt our overall productivity. So what we did is we collaborated, we brought and coalesced all these groups together, and now we have a single service that you can use whether or not you're touching it via Office 365, our cognitive toolkit, Cortana, Skype, you name it. Behind the scenes is a single service that services all of the NLP needs across Microsoft. And I want to dive into one item in particular, specifically our language modeling. This is state-of-the-art language models for both 1P and 3P. That's first party. Those are the things we use internally to process all of our data. But then also third party, meaning offering it up to the world through things like our cognitive toolkit. What we did was we said, well, geez, we've evaluated a bunch of deep learning models as we brought all these together. And the problem is we were still running into a lot of issues with the existing deep learning frameworks that we were using. Slow transition to production was a huge issue. It took a long time once brand new research came out, and NLP research is happening constantly. The APIs kept changing under the hood, meaning we had to, every time there was a new version, we had to go and rewrite all of our APIs and all of our testing and so on. And there was a real trade-off between high-level ease of use and flexibility. And so new data scientists and new developers who were coming through would end up taking a long time before they would be productive, and that just wasn't for us. So what we did is in partnership with Facebook, we worked through PyTorch, and we evaluated it as a potential option for us, and it immediately met our needs. We built our internal language modeling toolkit on top of PyTorch, and not just on top of PyTorch, but also using the native extensibility that PyTorch provided, we were able to build advanced and custom tasks and architectures that enabled us to meet our needs. It massively improved onboarding of new users, and it was an open and inviting community. And that meant that we could help move all of the advancements we were making internally upstream. As a result of all that work, we're able to scale those language modeling features to billions of words with very, very fast prototyping, so we're able to test brand new research papers and other things that come down the line. The API has been static and very well thought through from even 0.4, meaning our tests and our systems have been extremely powerful. And then we've seen a dramatic reduction in times and improvements in model sizes. And you can see some of the ways that we have moved that content upstream into the native PyTorch repo for everyone to use. And you can see some of those advancements here. But beyond that, beyond just PyTorch, we wanted to work and move this stuff to production very quickly. Today, or previously, we would have a problem where each group might spin up their own silo, and that was a real problem as well. Again, duplication, the amount of time it took to productionize, to package, and move those things was really, really hard. And while it made it very easy for our developers, it made it very, very hard on our SREs and the people who would have to support it. And you saw the just explosion in test matrices you see here. Now, I know what you're saying. Don't you love PyTorch? We do. We promise we love PyTorch. But we also love many other frameworks. We love R and TensorFlow, MXNet, scikit-learn. We can't pick and choose here. We want our developers to be most extremely excited. It's like trying to pick your favorite kid. It's my eldest. No, it's not. It's not, I promise. If you're watching this, it's not. Promise. So what we did was we worked with we worked with Facebook to go and launch the Onyx framework that enabled us to create an intermediate representation that meant we could take from any of these frameworks, convert it into this intermediate representation, and then roll it out to all of these various locations. And this massively improved the ability for us to move this to production. But it wasn't just about moving it to production. Like, though that's great, we also wanted to do a lot more here. And so we built a whole bunch of connectors. We have over 30 connectors right now. We saw a 14 times improvement in speed and latency characteristics. That's not 140%. That is 1,400% improvement. Just dramatic improvement, with the average improvement being between 3 and 5 times faster. And this is shipping on more than 1 billion devices today. Every time you open your Surface and you get that registration of what you look like and whether or not you can get into your machine, that is an Onyx model running on the Onyx runtime. And while it's 1 billion today, it's going to be 10 billion or 100 billion tomorrow based on the IoT and moving this out everywhere. And the fact is that we are so committed to open source. Everything you've heard me talk about here is open right now. You can go to any of these repos, the PyTorch repo, the Onyx repo, the Onyx runtime right now. You can download it. You can mess around, give us feedback, do pull requests. But most of all, you can contribute and just tell us how to make things better, because we are open and listening. And the reality is it's only through a deep and broad collaboration with a company as ready and understanding of machine learning as Facebook that we were able to achieve this. Thank you very much.
Thank you. We all know that PyTorch Onyx is your favorite child, okay? You can't say it, but that's okay. All right, next we're going to hear from Airbnb, talking about how they are using the conversational AI tools in PyTorch to develop smart reply that helps them actually provide a better customer experience. So Cindy Chin from Airbnb is going to come talk to us.
Good afternoon, everyone. I'm Cindy from Airbnb. I'm a senior data scientist at Airbnb. Today, I'm going to talk about Dialogue Assistant for customer service at Airbnb. Earlier this year, we welcomed our 500 millionth guest check-in on our platform. Airbnb serves a global community of hosts and guests. Customer service is an essential part of our business. Here is an overview of our customer service chat system. When a customer encounters a problem, they can either call us or contact Airbnb through their mobile devices and chat with a customer service agent. However, we observe some frustrations in the chat experiences. That's why we built Dialogue Assistant. First, we observed that agent would repeatedly type or copy-paste the same message over and over again, which is very time-consuming. Second, there exist some reply templates. However, over the time, they become hard to maintain, outdated, and very confusing to use. Third, agent at times can deliver an inconsistent experience through self-developed reply templates and grammar and spelling errors. So we built a smart reply feature to recommend quick responses based on customer's message. Agent, while chatting with the customers, can use these quick responses to suggestions to quickly respond to the customer. And the core of this product is powered by PyTorch. This is our thought process of developing our product. We first ask, what does an agent do in a conversation? There are two major tasks an agent does in a conversation. The first, keep an engaging and empathetic conversation. Second, help the customer solve their problems. Courtesy and empathetic messages play an important role in the first task, while the second task can be quite complex. When the customer is not able to self-solve their problem and is chatting with a customer service agent, The problem usually requires lots of domain knowledge and expertise from the agent to solve. So where should our solution focus? We decided to focus our solution on recommending courtesy responses. So we help the agent save time in their first task so they can be more engaged in actually solving the problem. We went through 3 stages in developing our solution. The first stage is to generate a pool of response candidates. What are the commonly used response candidates? What are the commonly used courtesy responses? What are their variations? How do they evolve over time? We leaned into the historical conversation between agent and customers. We vectorized all agent responses and clustered them into semantic clusters. This gives us a preliminary pool of response candidates. Our content experts then reviewed this preliminary pool to ensure proper tone and styles. This gives us a final pool of response candidates. Here are some examples of the clusters in this pool. You can see that each cluster contains variations of the same semantic meaning. This first helps us increase diversity. We can recommend different variations at different times. Second, this helps us reduce redundancy. We dictate that for recommendations appear at the same time, they have to come from distinct semantic clusters. The second stage is actually building the recommendation model. We treat this problem as a machine translation problem. We're translating the customer's input message into the agent responses message. So we're building a sequence-to-sequence model. We leveraged PyTorch open neural machine translation library to build this sequence-to-sequence model. PyTorch provides a lot of state-of-the-art technologies for us to accomplish this task, including various attention mechanisms and beam search. And the model trained using PyTorch is production ready. Using PyTorch has significantly speed up our model development cycle. And there is an active community in PyTorch around developing models for machine translation problems and conversational AI problems. It's worth to point out that the responses generated from the sequence-to-sequence model may contain incomplete sentences and unsatisfying styles. So we use the k-nearest neighbor to find their nearest neighbors from the candidate pool we generated in the last stage. We also ensure that recommendations appear at the same time, come from distinct clusters. So the model is production ready. The last stage is actually to productionize it. Airbnb's machine learning infrastructure, Big Hat, provides a service called Deep Thought. Deep Thought will deserialize the model and turn it into a real-time scoring API. When customer sends a message, this message goes to this API to get recommendations back in real time. This recommendation will appear on the agent tool for the agent to use. And we are open sourcing Big Hat framework. We have written a blog post on Airbnb engineering and data science blog. And we also published a paper at AI Deep Dialogue Workshop. These articles provide further discussions around further development steps and how we overcome various challenges during the process. If you are interested, please check them out. Last but not least, please stay connected with Airbnb by visiting airbnb.io for news, career, and events information. Thank you.
Thank you, Sunny. Thanks to PyTorch. Next, we're going to receive Daniel Bozinoff. He's going to talk to us about Genentech, completely different use of the same technology to really develop personalized cancer medicine using the key flexibility of PyTorch and the dynamic graphs. Daniel.
Hi, everybody. My name is Dan Bajanov. I'm with Genentech, and I feel really honored to be here today and share with you how we use PyTorch in drug discovery and in cancer therapy. Okay. This is, in a nutshell, all you need to know about the pharmaceutical industry. Of all the molecules, all the promising molecules, all the drug targets that we can come up with in research, only 3% actually make it to a final product. The vast majority of molecules get eliminated either in preclinical research or in failed trials transitioning from phase 1 to phase 2 to phase 3, et cetera. This is really a bad business model if you think about it. If we were an airline and we gave you a 3% promise to get you to the point that you bought a ticket for, this would not be a good business model. But it gets worse. This is, what you see here is the historical development of cost per single drug to actually make it to market over several decades. We call this Eroom's law, which is literally Moore's law spelled backwards. So where Moore's law improves over time exponentially, our cost increases over time exponentially. So this is, of course, you don't have to be a pharma expert to know that this is not sustainable. However, I personally, or we at Genentech, we see huge opportunity here for AI to actually reverse that trend and improve drug discovery as a whole. We have two strategies for this, one in drug discovery, the other one in drug development, where we develop deep learning models for specific domains to make some predictions about properties of molecules, about possible toxicity, et cetera. Basically predictions that we can get warned early on that something might not actually succeed in the end. The models can range anywhere from literature mining all the way to how a molecule potentially interacts with a given protein target. The other part of the strategy is to actually build composite models, so models of deep learning models. We figure that each of these deep learning models by themselves may be weak classifiers for a given prediction. However, when we combine them, and you've heard earlier today in the keynote also about multimodal learning, so we are applying this, and we have had great success by actually integrating all these different data streams or different modalities of data to actually get really good insights about whether patients might be responders or non-responders to a given therapy. But beyond that, we're also applying AI to see if we can come up with new therapies. And this is where cancer therapy comes in, specifically cancer vaccines as a potential. We've known for many years that every cancer is different. So even if the diagnosis is the same between two cancer types, they actually genetically might be different in their developments, in their properties, and in their behaviors, might be very different cancers. We've known this. We certainly know for a long time that two patients are very different. They have different physiologies. They respond very different to the same treatment. So as a company, how can we individualize medicines at scale and make it manageable in our industry? That's not trivial at all. And this is where AI can come to help. If we could identify unique molecules in cancer, specific to cancer cells, that are only produced by those cancer cells, we could potentially sensitize our own immune systems to attack those cancer cells and basically treat them like an infection. This is where we are using the immune system with the help of deep learning and PyTorch to build those models. What you see on the left is a T cell attacking an actual cancer cell. On the right is the molecule complex that is responsible for identifying those mutated molecules and presenting them on the surface of that cell so that an immune cell can recognize and destroy that cell. So in biological terms, there are 3 steps, or computational terms, there are 3 steps that this immunogenicity is comprised of. The first is where this MHC molecule actually identifies and binds to a mutant peptide. The second step is where the MHC presents that molecule on the surface of that cancer cell. And the third step is where a cytotoxic T cell recognizes that mutated molecule and destroys the underlying cancer cell. In terms of data, the data is unfortunately decreasing exponentially from step 1 to step 3. So we have initially focused only on step 1 and 2 to make predictions of which of these molecules are actually identified, to which the MHC is binding and which are presented. Our model architecture that we have used here is inspired by textual entailment in natural language processing. So basically where a text entails a hypothesis, and we have incorporated that into our composite model where we use partially a recurrent neural network as well as a straightforward feed-forward network, combine the outputs of these 2 networks, and predict at the same time the peptide presentation as well as the peptide binding. Now, important to point out here is that we're not using long-established tables of scores for individual symbols in a sequence. So we're treating these peptides as sequences, but each location has a different importance to a given sequence, and we're not using those score tables, but we actually have the data itself inform how important these individual symbols are to the overall peptide sequence. The results were very encouraging. So right out of the start, we've beaten the world standard in peptide prediction by a significant margin, as you can see here. But beyond that, we are now working on actually implementing transfer learning to actually tackle the third step in our sequence. So the third step, as I mentioned before, is very sparse in terms of data. We believe that by adding an additional input vector, by adding mutation positions, we can actually leverage everything that has been learned in step 1 and step 2 to come to the final holy grail of predicting immunogenicity. This will allow us to actually engage the immune system and produce vaccines that will attack cancer cells. PyTorch has been instrumental in all of this work. I could talk forever about how it's easier to debug, how it's natively Pythonic. This is actually really a big deal for us because our entire framework, our entire pipeline is standardized on Python. So it's really great to have another tool that is just naturally fitting in. But I really want to use this opportunity to thank all the PyTorch developers out there and just explain to them that their efforts really help saving future lives. So I really want to extend a huge thank you from an industry that you may have not thought about that is using this incredible tool, this incredibly available open source tool in an area where you may have not predicted. So thank you so much for all your efforts. And with that.
Thank you, Daniel. Really amazing to see PyTorch used to save future lives. Actually, our next speaker and our last speaker will talk also about saving lives, but in cars. This is Adrian Gaydon. He's going to talk to us about how Toyota Research Institute is using PyTorch.
Thank you, Jerome. Hi. Hi, everyone. So I lead the machine learning team at TRI, Toyota Research Institute. And to get started, the motivation for what we're doing. A user dies, like someone dies on the road every 24 seconds. That's a reality today. Another way to see this number is there's 1.35 million people that die in traffic fatalities per year. Sounds a bit surreal, but again, that's actually real. So now the question is why? Why is this happening? And so first, obviously cars go fast. and high-speed accidents are often fatal. Good infrastructure is incredibly expensive. The US interstate highway system costs roughly half a $1 trillion to build. I'm teaching you nothing here. Humans are fallible, right? They drink, they drive, they text, they don't rest enough. But also something that's really important is freedom. We drive a lot of places. In the US alone, it's like 1.2 trillion miles traveled per year. Trillion miles. So at TRI, we really want to tackle this problem head on, and we're working on it hard every day. We're using AI research for the future of Toyota's products around 3 main areas: safety, access, and quality of life. We have 3 main products in these areas. So around safety, we want to build an uncrashable car, human-driven car, which we call Guardian. In the access area, we want to make a car that is fully autonomous, and that's what we call Chauffeur. And eventually, we also are working on home robots that can improve quality of life. And so our strategy is really simple. While we're making progress on our long-term robotic challenges, some features we invent and develop can actually be gradually shipped today as new Guardian capabilities in production cars. And the real question is, why now? Was it a good time to work on this? There have been demos about self-driving cars since the late 80s, and current prototypes are very far from world-scale, like human-level driving abilities. And in the meantime, as I've shown before, traffic fatalities keep rising. So what has changed is deep learning, right? And this explosive pace of R&D in machine learning. And Toyota has actually a strategic advantage when it comes to machine learning, and that's what we call our data advantage. So Toyota is the #1 car manufacturer in the world. We have approximately 100 million cars on the road today, driven in any condition you can imagine and you can't imagine. Toyota is also selling 10 million new cars worldwide every year, and they all have cameras, they all have radars, they all have advanced safety features. And so cars constitute formidable data collection platforms before they will eventually become robots. And the volume of data generated, which can be like tens of petabytes per day, is going to dwarf YouTube by orders of magnitude. So that should get you excited and scared as machine learning people. Now, our key challenge as machine learning folks is how do we learn with this massive amount of data? And our main underlying hypothesis, which is the fundamental hypothesis behind machine learning, is performance improves with training dataset size. It's training dataset size, especially for deep nets. But there are some problems. First, this is true mostly for curated labeled dataset, right? Which is manually supervised learning. So you have human eyeballs that has to look at all the data. And Toyota has a raw data advantage from production cars, not labeled data advantage. And raw data cannot be labeled by humans at Toyota scale. It just simply cannot be done physically. So we need to invent new self-supervised and semi-supervised algorithms that can leverage the structure of this raw data at scale. So this is a must to complement the really tiny, tiny amount of human supervision that is available relative to the trillions of miles traveled every year. So our research agenda in this direction is what we call beyond supervised driving. And here, what you're seeing is an example of our recently published work on self-supervised learning of depth. Instead of using expensive active sensors like LiDAR, which are shooting laser beams, we trained a deep network with normal video data, right, so production data, and alone, right, just video data, to solve what is mathematically, geometrically, an impossible problem, which is predicting how far things are from a single monocular image. And this doesn't use geometry to make the solution, because this is actually impossible. This uses geometry as a statistical learning objective to train that deep net. And what you're seeing here is this 3D reconstruction of the world from a single image. And this is what we call a pseudo-LiDAR, which we call super depth in our paper, and is an example of self-supervised learning that is cutting-edge research, but also really important for production at scale. And so to iterate fast on these ideas and to be lean, we need like really good tools to operate at world-scale data. And typically, the academic research community, like in computer vision, we use like 32 by 32 pixel images like MNIST and SciFar. Even ImageNet is small by today's standards, right? So the problem, though, is that experimental observations on these data sets are not guaranteed to transfer to more realistic ones for driving. So that's why, although we are a research team, the first thing we did is we developed a cutting-edge cloud platform for distributed deep learning on high-resolution sensory input, especially video. So here's a graph of our GPU usage as we scaled up over the years and as we gradually developed these tools. And maybe you can guess when we started to introduce PyTorch and when we had a really nice Christmas break and a nice productivity boost afterward. And really, like for us, PyTorch's unframework nature has really led to its successful adoption at TRI. It was instrumental in scaling up the simple APIs, the defined by run paradigm, the integration with the global Python ecosystem, and overall the great user experience for fast exploration. And it's not just fast to develop, right? It's also really fast for training at very large scale, as you can see here. So now talking about going fast, the pace of progress in AI, as you all know, is really incredible. AI research is done in the open, as it should, and Facebook is a great leader in that field. However, the field of automated driving is notoriously secretive. There's a lot of hype with very little actual published research by the key players. So we're different. While we care about having an impact as fast as possible, because the clock is ticking, we are seriously facing the long-term challenges and publish our progress. So this graph right here describes the growth in terms of research publications in automated driving and deep learning that my team has done. And in addition to our creativity and expertise, PyTorch has really amplified our capabilities to iterate quickly from idea to real-world use cases. And real-world use cases in driving is really hard. Like fast real-world transfer is hard for robotics in general because it requires extensive testing. And improving one's tools and good architecture is essential, and what in Toyota we call like Kaizen, continuous improvement journey. And this is why we're excited for new awesome PyTorch production features that will help accelerate us even further. Let me drive you through a quick example of how things can go from an idea to a real-world use case. So remember the accident statistics that I showed you earlier? Well, this is a daily reality for us. This is one of our manual data collection run here in California on I-80. This is a high-speed crash on the highway that happened at 70 miles per hour. Luckily, nobody was hurt because our safety driver, Trevor, is really well-trained. Now, we saw this, and we wondered, can our current autonomy stack, right, the AI algorithms we develop, planning, control, prediction, perception, et cetera, can it be quickly repurposed into a guardian feature that would prevent this type of accidents? So first, we set out to recreate this particular event in simulation from our driving logs. And what you can see here, what actually happened. Then we reused our current technology to add a predictive, not reactive, a predictive driver assistant feature that basically uses our advanced perception and planning capabilities to trigger an intended acceleration and avoid the collision altogether, because it understands the world around it, and it can predict and forecast the trajectories. So we validated this, of course, not just in simulation, but in actual car on closed course, because when you develop safety features, you don't use users on the public road to test. So at least the serious people do. And beyond simulation, this is a mandatory step. So here, what you see is this guided soft target, right, that simulates the one that's going to collide, and we check that the car is going to accelerate. We actually developed this in-house also very quickly, so that's pretty cool. So that's just an example, right, to show you how we can really quickly iterate between research and real-world applications, and we're really excited for what's to come. So you'll see more next year at a big event where we will showcase more things like this. And this is our latest platform 4. It's our latest super cool car, which you'll see at CES, at CPR, and in other events soon. Thank you.
Thank you, Adrian. Well, I want to thank you again, all our speakers, Microsoft, Airbnb, Genentech, and Toyota. It's pretty amazing to see all these use cases. I mean, we saw speech recognition, we saw smart reply, we saw new treatments for cancer that are personalized, and we see self-driving cars, okay? It's a pretty amazing ecosystem that's building around PyTorch today. I also want to thank Michel Miner, who actually put together this lineup and is supporting our developer community. And I want to thank you all for your time. If you want to talk to the speaker, they're right here. And enjoy the rest of the conference. Thank you.